I'm Salonic Resh. This is Mouse, Inference and Non-volatile memory for energy harvesting applications. All of the authors are from the University of Minnesota. So this is the outline. So first I'll provide some background and scope for the work. Then I'll cover the memory devices that Mouse uses, and then cover the computational substrate that we're using. And then I will go over the Mouse architecture. The most critical part is the Correctness Guarantee, which I'll cover next, and then I'll cover the details of the evaluation. So before getting into the true substance of the work, I'd like to make a brief analogy. In celebration of this paper being accepted, a family of mice have moved into my apartment this summer. And this is an actual photo of one of my current roommates. So living with them has been an adjustment, but I realized they actually make pretty good energy harvesting machines. They are able to perform complex tasks such as object recognition. They have very acrobatic skills such as the ability to climb furniture. They harvest energy from the environment such as consuming unsecured food. And then they're able to communicate, like telling their friends where all the food stores are. Mice are organic energy harvesting devices, but we'd like to build electronic ones. These are devices that operate without batteries, so they harvest energy from the environment, such as with solar, RF, or thermal energy. But these power sources are unreliable, or even if they are reliable, they may be insufficient to power the device continuously, and hence the device has to operate intermittently, meaning it's going to have to shut off to collect power and then only turn on when power is available. So a direct result of this is that the device is going to have to continuously or periodically back up its state by saving it to non-volatile memory to prevent total loss of information on shutdown. However, this introduces conflicting requirements. You would ideally like to frequently checkpoint to prevent much work from being lost on shutdown. However, this checkpointing consumes precious energy resources as well, which for these devices could be in very short supply. So in this work, we show how processing in non-volatile memory can provide some ideal solutions to this problem. First, since the computation is happening within the memory itself, the data backup is automatic, instant, and permanent. Additionally, these operations are highly energy efficient, and also high degrees of parallelism available enable significant performance as well. So now I will cover the memory devices that Mouse uses. Mouse uses magnetic tunnel junctions, or MTJs, which consist of two magnetic layers, a fixed layer and a free layer, which are separated by a thin insulator. It has two distinct states, a low resistance state, which is assigned to logic value 0, and a high resistance state, which is assigned to logic value 1. The state of the device can be changed by passing a sufficiently high current through it. Quite importantly, the state that it transitions to is determined by the direction of the current. So if electrons flow from the free layer to the fixed layer, it sets it to the high resistance 1 state, and if they flow from the fixed layer to the free layer, it sets it to the low resistance 0 state. So by connecting MTJs in circuits, we're able to perform logic operations. And all logic operations are performed via thresholding, so the state of the output MTJ either switches or not depending on the state of the input MTJs. And using this approach, we're able to implement a universal set of gates, including NOT, NAND, and NOR and OR. For example, a NAND gate has an output of 1 unless both of the inputs are 1. So if we want to implement this with MTJs, we'll have our two input MTJs in parallel, which are then in series with our output MTJ. And note that the output MTJ must be preset to 0. We will then apply a voltage across V1 and V2 such that electrons flow from the input MTJs to the output MTJ. In the case where either of the input MTJs is in the low resistance state, it will allow sufficient current to travel through the output MTJ to enable it to switch state. In this case, since electrons are flowing from the free layer to the fixed layer of the output MTJ, it will switch to the 1 state. However, if both of the input MTJs are in the high resistance state, it will not allow enough current to change the state of the output MTJ, and hence it will remain at 0. So after this has been performed, we can see that the output MTJ state is the logical NAND of the two input MTJs. I will now cover our substrate. We are using Computational RAM, or CRAM. It is essentially a STT-MRAM array with some minor modifications. These modifications include 1 extra bit line per column and 2 additional transistors per row. So in each column we have 3 bit lines. Bit line even is shown in black, and that connects to MTJs on even rows. Bit line odd is shown in blue, and that connects to MTJs in odd rows. And shown in green is the logic line, and this connects to all MTJs in the column through the access transistors. And the access transistors are controlled by the word lines, which are shown in red. This architecture allows us to perform logic gates inside the array, quite notably without the use of the sense amplifiers. So for example, if we drive word lines 0, 1, and 2 high at the same time, we can connect MTJs in rows 0, 1, and 2 to the logic line simultaneously. Then if we apply a voltage across bit line even and bit line odd, this effectively creates the same circuit shown earlier for the 2 input logic gate. In this case, the input is in rows 0 and 2, and the output is in row 1. Only one logic operation could be performed in a column at a time. However, we can perform logic in many columns simultaneously. The only restriction is that these simultaneous logic operations must have inputs and the output on the same row, because the word lines dictate which rows are active. So exploiting this parallelism allows us to achieve significant performance, and as our gate set is universal, we can perform arbitrary computation. I will now explain the mouse architecture. Mouse consists predominantly of CRAM tiles, which are 1024 by 1024 arrays. Some are dedicated for data, while others are dedicated for holding instructions, though their structure is identical. Mouse also has a simple memory controller, which is responsible for orchestrating the operations. It reads instructions from the instruction tiles, decodes them, and then broadcasts them to the appropriate data tiles. Also inside the memory controller there are multiple copies of the program counter and other non-volatile registers. These are responsible for keeping mouse intermittent safe, though that will be explained in more detail later. Mouse implements a very simple instruction set. There are only 3 types of instructions. There are memory operations, which are the standard read and write. There are logic operations. These correspond directly to individual logic gates, so there's an instruction for NOT, there's an instruction for NAND, and etc. There is also an instruction dedicated for peripheral circuitry control, the activate columns instruction. This instruction determines which columns have logic implemented in them when an instruction is issued to that tile, though I will not cover that and refer the interested person to the paper for more detail. I will now cover the correctness guarantee. As the power source is unreliable, we often lose power and have to shut down, and when this happens, we revert to the last save checkpoint. To maintain correctness, the transitions between checkpoints must be idempotent, meaning that if they're reperformed multiple times, the same result must be achieved. This implies that unexpected power outage during this transition cannot corrupt any of the data or the architectural state. In mouse, checkpoints are created after every instruction. This would be inefficient for more traditional systems, but it is appropriate for a PIM-based system as the data backup is happening regardless, and we're just taking advantage of that. So for mouse to maintain correctness, the individual instructions must be idempotent. There are 2 components to this, making sure that the logic operations themselves are idempotent and that the transitions in the memory controller are idempotent. To guarantee that logic operations are idempotent, we have to consider all possible cases when a power outage interrupts an operation. As there is only a single event in each operation, which is the switching of the output MTJ, there are actually only 2 times to consider, pre and post switching. The other consideration is whether the output MTJ should switch or not, depending on the value of the inputs. So this results in 4 different possibilities: whether the interruption happens before or after the switching event, and whether the switching event should occur or not depending on the inputs. So now that we have our 4 cases, we can analyze what happens when we reperform the operation. So looking first at the case where the output MTJ should not switch. If it did not switch before the interrupt, well, none of the inputs have changed, so reperforming this operation is identical to performing it the first time. And then again, there will be insufficient current to cause the output MTJ to switch, so we will get the correct output. In the case where it did switch before the interrupt, well, this is actually not possible because we were not supplying a current which was sufficient to change the state of the output MTJ, so this is a case that we don't have to worry about. Now looking at the case where the output MTJ should switch. So if it did not switch before the interrupt, this is again the case where none of our inputs have changed. So reperforming the operation is identical to performing it the first time. So if we are not interrupted, we will be able to finish, we will cause switching of the output MTJ, and we will get the correct result. In the case where it did switch before the interrupt, now this is where our inputs actually have changed. But it turns out this is still fine because the state that the output MTJ switches to depends on the direction of the current. So if we reapply the operation, it will not cause the output MTJ to revert back to its original value. It'll stay at the value that it was set to before the interruption occurred. So turns out in all 4 cases we get the correct result. So performing a logic operation is idempotent and therefore intermittent safe. The second condition required to guarantee correctness is idempotent state transitions inside the memory controller. I leave the details to the paper, but due to its relatively simple nature, its architectural state can be saved in just a few non-volatile registers. This includes 2 copies of the program counter and a parity bit to determine which copy is valid. Now we can cover the evaluation. For applications, we chose binary neural networks and support vector machines. These are lightweight machine learning algorithms which are still capable of solving useful problems. For benchmarks, we use MNIST for image recognition, and human activity recognition is taking accelerometer and gyroscope measurements from a smartphone and classifying the activity the person is performing who's carrying the phone. Our baseline for comparison is the energy harvesting accelerator Sonic, which uses neural networks to solve the same benchmarks. Different energy harvesters in different environments will be able to supply varying levels of power. Sonic was tested assuming an average consumption of 5 milliwatts. We test mouse over a wide range of power sources, from 60 microwatts up to 5 milliwatts. We can plot the latency for each benchmark to complete versus the power that the device is able to consume. If we plot the Sonic points, they are at the 5 milliwatt level, and as MNIST is a slightly larger benchmark than human activity recognition, it takes slightly longer to complete. But if we plot the points for mouse, we can see that if it consumes anywhere near as much power as Sonic, it has a greatly reduced latency, so we can conclude that mouse has significant latency advantages. For energy efficiency, there are a few intermittent specific benchmarks. The backup energy, which is the energy dedicated to storing the architectural state to prevent total loss on shutdown. The dead energy is the redundant computation you perform on restart. And restore energy is the energy required to bring the device back online. And ideally you want these to all be quite low. The logarithmic energy dedicated to the total and each of these metrics for mouse is plotted on the right. And as it can be seen, the backup, the dead, and restore energy are all very small fractions of the total energy, which shows that mouse is well suited to operate in this domain. For total energy efficiency, for MNIST, Sonic takes 27 millijoules, whereas mouse takes only 1.4. And for human activity recognition, Sonic takes 12.5 millijoules, whereas mouse only requires 0.47. Hence, that we can conclude that mouse is also extremely energy efficient. So in conclusion, processing in memory can alleviate data backup overheads by having the data automatically stored in memory with each operation. Logic performed with MTJs is inherently idempotent, making it naturally well suited to operate in the energy harvesting domain. And both of these principles combine to enable energy efficient, high performance, and intermittent safe accelerators. That brings me to the end of this presentation. I'm Salonic Resh. Thank you.